So welcome back. So the last lecture was foundations, variation, standard deviation, the z-score, the two kinds of error. Today we spend it. Three things: how to actually build a control chart from raw data, how to read the patterns inside the limits, and how to answer the question a control chart cannot. Is this process good enough? So fair warning on the pacing. The first two-thirds of today is mechanical. There are formulas, there are lookup constants, there is arithmetic. That is generally how the methods work, and I would rather see you do the machinery than take it on faith from the software. But the mechanics is not the point. The point is judgment. Which charts, which subgroup, which rules, and what the resulting number is resulting number is actually entitled to tell you. I'll flag the judgment calls as we hit them, and every one of them will show up in your homework. So 5 things by the end: build the X bar R chart from the raw subgroup data and read the two charts in the right order. That ordering is not a stylistic preference. Get it backwards and the second chart is meaningless. Choose the right chart for the data you actually have in the fab. That is not the data you'd like to have, and the constraint is metrology cost. Interpret the run rules and name the physical mechanisms each pattern points at. That is the part that makes you useful in the fab. Anyone can read the alarm. Knowing that a sawtooth means seasoning and an alternating pattern means two-chamber is the skill. Explain what it costs to add a rule, every rule by sensitivity with false alarm. And compute CP and CPK and say precisely what each does and does not tell you. The last clause is where the marks are. So 4 things from the last class we used today. Variation has 2 causes. Common cause is the system operating normally. Special cause is the event. They demand opposite responses, and confusing them is expensive in both directions. Sigma is the distance and the typical gap between the measurement and the mean in the units you measured. We built it in 5 steps. The z-score is the universal ruler, distance from the center in units of sigma. And I promised you that control limits, capability, and parts per million are all 3 same z-score wearing different names. Today, 2 of those 3 will show up. And 3 sigma is a choice, not a law. 0.27% false alarms, 1 per 370 points, Schuhart's economic compromise. Today, we turn the last 2 into an actual chart. 3 questions, and the order is strict. Is it stable? Does the process behave today as the way it behaved yesterday? That is the control chart, and it occupies most of today. What is it telling me? A signal is not a diagnosis. Which pattern appeared and which class of physical mechanism does the pattern point at? That is the run rules. And only then is stable good enough. Is the natural behavior of this process tight enough to meet the tolerance? That is capability. You may not skip forward. Computing a capability index for an unstable process is meaningless because there is no single distribution to compute it from. The mean is moving, the spread is moving, and whatever number you produce describes a mixture that will not exist next week. The anatomy: 3 lines and a decision rule. The center line is the process average computed from the data, not from the target. The distinction matters. If your process runs consistently high, the center line sits high and the chart is monitoring the process you have rather than the one you wanted. The upper and lower control limits sit at the plus and minus 3 sigma of the plotted statistic. Note the phrase of the plotted statistic. If you're plotting subgroup means, it is 3 sigma of the mean, which is 3 sigma over square root n. That factor is the whole reason subgrouping helps. The rule: a point outside a limit is a signal to investigate. Everything else is common cause noise and you leave it alone. The restraint is have the value of the chart. Before we build anything, the assumptions, 4 of them, and every one fails somewhere in the fab. The plotted statistic is roughly normal. True for subgroup means thanks to the central limit theorem. Much shakier for individuals and shakier still for counts at low defect rates. Consecutive points are independent. Frequently false. Chamber state carries over between runs, and a run-to-run controller introduces correlation deliberately. Sigma is constant while you are watching. R is specifically the test of this, which is why we read it first. And the measurement system is trustworthy. Every sigma on today's slide includes metrology tool's own variation, and we will not separate them until the 3rd lecture. The chart still works when these are approximately true. Knowing which one is failing is how you debug a chart that misbehaves and that is a much more useful skill than knowing the formulas. This is the common error in the field and it deserves the time. Control limits are computed from the process. They describe what the process actually does and nobody chooses them, they fall out of the data. Specification limits are handed to you. A designer decides that below this threshold a transistor does not switch fast enough. A customer wrote it in a contract. They have nothing whatsoever to do with what your tool is capable of. Schuhart's phrasing is the one that sticks. The control limits are the voice of the process. The spec limits are the voice of the customer. They are unrelated. Spec limits can be wider than the control limits, which is the happy case. They can be narrower, which means that you are shipping scrap on a perfectly stable process, and they can sit anywhere in between. Never draw spec limits on a control chart. I'll tell you exactly why in a few slides. 2 independent access, 4 situation, 4 completely different job. In control and capable, the goal, the stable and comfortably inside the spec. Job, leave it alone and keep monitoring. In control and not capable, predictable and predictably making scrap. That is nothing to investigate because nothing is wrong in the special cause sense. The process is doing what exactly what it always does, and what it always does is insufficient. Job, change the system. Out of control but capable, you are getting away with it. The margin is wide enough to absorb the excursions for now. Job, find the special cause before the margin runs out. Out of control and not capable, firefighting, and you cannot even predict how bad tomorrow will be. Job, stabilize it. Capability is not yet a meaningful question. Stability and capability are independent. Collapsing them into one axis is a single most common conceptual error in this field. A point inside the control limits can still be out of specification, and a point outside the control limits can be perfectly sellable. Both have surprised people, so let me be concrete about each. First off, a process that is beautifully in control with tight limits sitting badly off target will produce in control points that are outside the specs all day long. Chart is not lying, it is answering a different question. Second half, a process with enormous margin can throw a 0.3 sigma from its center line and still be nowhere near the spec limit. You investigate because something changed, but you do not scrap the lot. This is why you never draw spec limits on control chart. The moment they are on the same picture, every conversation becomes about spec and the run rules become invisible and operator starts adjusting to the wrong lines. 2 distinct jobs and the software will happily let you confuse them. Phase 1, establish the limits, collect 20 to 35 subgroups from a period you believe were stable. Compute trial limits, investigate every point that fails and remove it only if you find a documented assignable cause. Recompute and iterate until what remains is clean. Notice that phase 1 is not a calculation. It is an investigation with a calculation attached. Phase 2, monitor, freeze those limits and plot new data against them. Do not recompute the limits because the process moved. That movement is the signal you build the chart to detect. Recomputing is how you delete it. Limits computed from contaminated data are the most common reason a chart in a real fab never fires again. It looks professional and it reviews weekly and it is completely inert. 3 practical questions about phase 1. How much data? 20 to 35 subgroups is a conventional minimum. Fewer and your limits carry so much uncertainty that they are close to arbitrary. And the same confidence interval problem we will hit again with CPK at the end of today. What may I delete? A point with documented assignable cause, a logged recipe error, a failed qualification, a known bad material lot. There should be a record you can point at. Never a point that is merely inconvenient. You cannot find a cause, the point stays and your limits are wider, that is honest. When do I recompute? After a deliberate process change, a new tool, a new recipe, a chamber rebuild. This chart keeps alarming. So we widen the limit. Is the single most destructive sentence in industrial SPC. It converts a working detector into wall decoration and everybody involved feels they solved the problem. Here is the question that looks pedantic and is not. We need sigma to set the limits. Why not compute just the standard deviation for all the data, because it is wrong and it fails in the wrong worst possible direction. Suppose the process shifted during your baseline period, which is exactly the situation you're trying to detect. Pull everything and that shift is absorbed into the estimate. Sigma comes out too large. The limits come out too wide and the chart becomes blind to the very thing it inflated it. Estimate is contaminated by the signal. So we estimate sigma within subgroup variation only. Sigma hat equals R bar over D2. That range within the subgroup is a short-term measure. It has no opportunity to observe drift between subgroups. Short-term variation says the limit. Between subgroup variation is what the chart is trying to detect. Never let the second contaminate the first. These are the numbers you look up, and I want you to know what they are so they stop feeling like magic. D2 is the expected range of n draws from a standard normal distribution. That is the entire definition. If you take 5 values from a normal distribution with sigma equals 1, the average range is 2.326. So divide your observed range by 2.326 and you have an unbiased estimate of sigma. A2, D3 and D4 are just algebraic shortcuts. A2 folds together the 3 and the root n and the D2 so that an operator can write the x double bar plus A2 R bar and be done. No square root on the factory floor. Look at D3. It is 0 until n equals 7. Below that, the lower control limit of the range chart is 0. With small subgroups, a range of nearly 0 is not statistically surprising. There is nothing to flag. 2 questions and the chart is chosen for you. Is the data continuous or attribute? If it's continuous, is n greater than 1? Continuous with n greater than 1, x bar and r for subgroups up to about 10 and x bar and s above that. This is the most sensitive option and you should use it whenever the metrology budget allows you. Continuous with n equal 1, individual and moving range. This is the fab workhorse, and as we had established in the last class, the chart with the weakest assumption. Uncomfortable but true. Attribute P and NP for proportions and C and U for counts. Notice what actually determines the answer. It is not statistics. It is how many measurements you can afford and which is a metrology capacity decision made by someone else. The statistics then tells you what you are entitled to conclude from what you got. Before we compute anything, the subgroup. This is the design decision that determines everything and it is not a statistical question. The rule from last class, whatever varies inside the subgroup becomes the noise the chart is measured against. Sources of variation inside the subgroups set the limit. Sources between subgroups are what the chart detect. 5 sites on one wafer. Within the subgroup variation is the tool's radial signature, so your limits are calibrated against within the wafer non-uniformity. The chart will catch anything that moves the whole wafer and will be statistically blind to the changes in the signature itself. 1 site on each of 5 wafers. Within subgroup variation is wafer to wafer variation. Different limits, different blind spots. Same n, same arithmetic, different charts. Decide what you want the chart to be blind to. The decision is the subgroup. Get it wrong and every number downstream answers a question you did not ask. A subgroup is a set of measurement you agree to treat as one sample. That is the whole definition. Everything else today depends on it. Here is one lot in the left. 25 wafers went through the etcher. Metrology time is expensive, so 5 of them get measured, 1 site each. That gives 5 numbers: 44.67, 46.06, 44.67, 45.30, 44.99 nanometers. Those 5 measurements are one subgroup and the number of them, 5, is called n. That is all n ever means in this course, the subgroup size. How many measurements go into one plotted point? You will see everywhere from here on the x bar limits use A2, which depends on n. Sigma hat uses D2, which depends on n. the limits are tighter by root n. Every one of those is this number. Now the middle panel. We now collapse them into two numbers. The mean x bar is 45.06. The range r is 46.06 minus 44.55, which is 1.51. And those two numbers become 1 point in each of two charts, 1 point per lot. So over 30 lots, 125 wafer measurements become 60 plotted numbers. Every individual values are never plotted again. They have done their job by contributing to a mean and a range. That compression is not a loss. It is what makes the pattern visible. Nobody can read a table of 125 numbers. Everybody can read two charts. Here is where it stops being bookkeeping. Both of these have n equal to 5 from the same fab on the same parameter, same n, same formula, same constants. The arithmetic is the character for character identical. The left one. Option 1, 5 sides on a single wafer, center and 4 points towards the edge. Option 2, 1 side on each of the 5 wafers from the same lot. Do these two give you the same chart? They do not. And the reason is the most important idea in this segment. So n does not specify a subgroup. N tells you how many. It says nothing about which 5, and which 5 is what decide what the chart can see. Look at what varies inside each subgroup. On the left, 5 measurements differ because of center to edge non-uniformity, the tool's radial signature. That is what R measures, and that is what sets the control limits. On the right, the 5 measurements differ because of wafer to wafer variation within the lot. Completely different physical mechanism, so a completely different R bar, so completely different limits. And each of it is blind to the other. The left-hand chart cannot see the change of the radial signal because that signature is already inside its own noise estimate. Fab variation is nested. Sites within a wafer, wafers within a lot, lots within a chamber, chambers across the fleet. Each level contributes variance. Your subgroup draws a line through that hierarchy. N tells you how many measurements you take. Where you take them decides which level of this hierarchy land inside the subgroup and which land between subgroups. Whatever falls inside the subgroup becomes the noise the chart is measured against. Whatever falls between the subgroup is what the chart can detect. Same wafer, same 0.55 nanometer shift at lot 10, 2 subgrouping choices. 5 sites on the wafer puts within wafer variation inside the subgroup. Within wafer is the biggest term, so R bar is large, so the limits are wide and the shift is absorbed, nothing fires. 5 wafers from one lot puts only wafer to wafer inside. R bar is small, the limits are tight, the same shift is caught immediately. Same wafers, same n, same arithmetic, different chart. So the question to ask before you build any chart is not what my sample size is, it is what I want this chart to be blind to. That decision is the subgroup, and it is a process engineering judgment, not a statistical one. So now the 6 steps. You will do exactly this in the homework by hand once and then never again. Range of each subgroup. Average range, grand average, R chart limits from D3 and D4. Check the R chart, X bar limits from A2. The 5 step is not a formality. Look at where X bar limits come from. X double bar plus or minus A2 R2. The limits on the mean chart are computed from the average range. So if the range chart is unstable, if within subgroup spread change during your baseline, then R bar is not describing a single consistent process, and X bar limits built from it are meaningless numbers. This is why you always need to read the R chart first, not convention, dependency. And I'll show you what it looks like when people get it backward in a few slides. Real numbers, gate CD, 25 lots, 5 wafer measured per lot, one side each. So within subgroup variation, here is wafer to wafer within lot. Specification is 43 to 47 nanometers. R bar comes out to be 0.98 nanometers. So sigma hat is 0.98 over 2.326, which is 0.42 nanometers. Note this, that 0.42 is our estimate of the short-term process sigma, and we will use it again at the end of the lecture for capability. It is the same number doing both jobs. X double bar is 45.19, slightly high against the 45 target, and hold that thought. X bar limits 45.19 plus or minus 0.577 times 0.98. That gives 44.62 to 45.75. R limits 0 to 2.115 times 0.98, which is 2.07. Look at how far inside the spec window these control limits are, and the process lives between 44.6 and 45.8, and the specs allows 43 to 47. That gap is capability, and we will measure it properly at the end of today. Here is what raw data actually looks like. 10 of the 25 lots, 5 wafers each. Nothing is surprising. The numbers hover around 45, they wobble by a few tenths, and nothing jumps out as obviously wrong, which is the point. And you can read this table. You cannot read this table, nobody can. Look at the last two columns, X bar and R. This is what a shoe chart, this is all a shoe chart ever uses. R chart first, always. 25 points, each one a range of 5 wafers within a lot. The center line is 0.98, upper limit at 2.07, lower limit at 0. Subgroup 25 fails, the spread within that lot is roughly doubled. Now notice what this tells you and what it doesn't. It says nothing about whether the lot was on target. It means those 5 wafers might be exactly 4.5. What changed is the agreement between the wafers in a single lot. What would that do? A chamber with a developing non-uniformity, a wafer loaded in a bad position, a metrology tool drifting mid-lot, a single wafer within a genuine defect dragging out. That last one matters. The range uses only the max and the mean, so one bad wafer moves it entirely. Worth checking before you launch an investigation into the chamber. Now and only now, the X bar chart. Subgroups 18 and 19 sit above the upper control limit, and the process center moved, and the moved for at least 2 consecutive lots, which makes it one of measurement error unlikely. Look at the size. It's about 1 nanometer on a chart whose limits are about half a nanometer wide. That is a substantial shift in process terms, and it is completely invisible against specification, which allows 4 nanometers of total range. So on a real line, hold the affected lot, check whether the shift persists in lot 20, and start at the maintenance and recipe logs for shift covering lots 18 and 19. The chart has given you a magnitude and a direction and a timestamp. It hasn't given you a cause yet. The pair as it is always used. X bar on top, R underneath, sharing x-axis so you can read them down a column. 2 independent signals in this data. Around the subgroup 22, the spread blew out, visible only in the bottom chart. Around 18 and 19, the center moved, visible only at the top. Neither chart alone would found both, and this is why they are always paired. They are signaling different questions about the same subgroups. Has the process moved, and has it become less consistent? In practice, the R chart often moves first. Equipment tends to get erratic before get biased. A degrading seal, a valve starting to stick, a wafer handler losing repeatability. All of those widen the spread before they shift the mean. So the bottom chart is frequently your early warning, and the top chart is the consequence arriving later. Let us be precise about what each chart is sensitive to. The X bar chart watches location. Has the center moved? It catches recipe drift, and a wrong offset loaded chamber to chamber mismatch, a controller overcorrecting, temperature drift. It is blind to a change in spread provided the mean stays put and the blindness is total, not partial. The R chart watches the spread. Has within the subgroup variability changed? It catches a degrading chamber, increasing non-uniformity across the wafer, an unstable metrology tool, or one bad wafer in the lot. So the practical point now, the R chart often moves first for the physical reason I just gave. A tool usually gets noisier before it gets biased. So the R chart is the early warning and the X bar chart is the consequence. If you are only going to look at one of them in a hurry, and people do, look at the one that moves first. Here is what going in the wrong order costs you. Same process, but at a subgroup 13 within lot spread more than triples. This mean does not move at all. The X bar chart shows nothing, not a single point outside the limit, no run rule violation. If you looked at it alone, you would sign off and go home. But the R chart is screaming. Now, why is the X bar chart silent? Because the limits were computed at X double bar plus or minus A to R bar. And the R bar was inflated by the very excursion we are trying to see. The chart widened its own limits to accommodate the problem. The X bar chart cannot detect a spread change. It is not that it is bad at it, it is structurally incapable because the spread is an input to its own limits. That is the dependency, and that's why the ordering rule exists. A short note on X bar and S charts. Why does the range work at all? Because within the small subgroups, it uses most of the information. At n equal 5, the range is about 95% as efficient as standard deviation. You give up 5% and gain the ability to compute it in your head. Why does it stop working? Because the ranges only ever uses 2 of the n values, no matter how large n gets. At n equals 5, it ignores 3 values. At n equals 20, it ignores 18. By about n equals 15, the efficiency loss is material. So above roughly n equals 10, switch to S, sigma hat equal S bar over C4. You will rarely need this because metrology costs keep n small. Where you do see it is automated inline metrology, integrated thickness, or reflectometry, where measuring 49 sites costs essentially the same as 5. There, use S. 4 ways to get this wrong, and they are all none of them makes the chart look broken. Reading X bar chart first, you just did this once. The limits are built from R bar, so if the spread moves, the mean chart is decorative. Putting spec limits on the chart. Now every conversation is about spec. The run rules become invisible against the much wider lines, and the operators start adjusting to the customer's number rather than that of the process. Recomputing limits when it alarms. You have deleted the signal. Limits change after a deliberate process change, never in response to the data you did not like. Subgrouping by convenience. Whatever the metrology recipe happens to measure, it is not a rational subgroup. It is a default that someone chose for throughput reasons. Notice that 3 of these 4 make the chart less sensitive without making it look broken. This chart still gets printed, still gets reviewed, quietly detects nothing. That is the worst. That is worse than having no chart because you believe you are covered. How fast will it actually notice? Average run length, the number of subgroups until the chart fires. With n equals 5, 1 sigma shift takes about 5 subgroups to detect. That is reasonable. A half sigma shift takes over 30, and that is bad. If you chart daily, half sigma shift runs for a month before the chart says anything. The Shewhart chart is genuinely poor at small sustained shifts. This is its main weakness, and it is structural. Each point is examined in isolation with no memory of the points before it. A run of 20 points, all slightly high, is, to rule 1, 20 independent unremarkable observation. 2 ways out. Run rules, which give the chart a limited memory and we do those this afternoon. And generally memory-based charts, EWMA and CUSUM, which accumulate evidence across points. Those are lecture 3 and they are dramatically better at exactly this case. Now the case that actually dominates in fab, n equals 1. 3 reasons you end up there. Metrology is the constraint. A CDSEM measurement takes minutes and the tool has a queue behind it. Going from 1 wafer per lot to 5 is a 5-fold increase in demand on the scarcest resource on the floor. Very often the answer is a no. Some measurements are destructive. Cross-sectional TMs, seams profiles, certain electrical test. You get one number and the wafer is gone. There is no possibility of a subgroup. Some quantities are singular by nature. Bath chemistry concentration, chamber pressure at a set point. There is one valve per lot because there is only one thing being measured. No subgroup means no range within a subgroup. No range means no R-bar, and no R-bar means we lost our estimator for sigma. So we need another one. The trick is neat. Treat each consecutive pair of lots as a subgroup of 2. The moving range is the absolute difference between neighboring measurements. Average those, divide by D2 for n equals 2, which is 1.128, and you have an estimate of sigma. Why is this the right instinct? The logic is the same as before. We want a short-term estimate. The difference between two adjacent lots has very little time in which to absorb the drift. If the process is slowly wandering, consecutive values are still close together, so the moving range stays small and the estimate stays short-term. Exactly what we want for setting limits. Now the caveat, the flag is hard. But look at the assumption hiding in there. Consecutive lots must be independent. If they are correlated, and in the fab they often are, the moving range is systematically too small, sigma hat is too small, and the limits come out far too tight. And we'll see what that looks like in a few slides, and it is dramatic. Same process, same sigma, 5 different choices of n. Only thing is changing how many measurements go into one plotted point. At n equals 1, the limits sit at 3 sigma. At n equals 2, plus minus 2.12 sigma. At n equals 5, plus minus 1.35 sigma. At n equals 10, 0, plus minus 0.95 sigma. Every one of those is 3 sigma over root n, and you can see the band closing as n grows. A shift that is invisible at n is unmissable at n equals 10. Same process, same shift, different charts. Note the diminishing returns. But look at the spacing. Going from 1 to 2 buys you a lot. From 5 to 10, doubling your metrology load takes you from 1.35 to 0.95. That is why 4 or 5 is near universal. It is where the curve flattens against what metrology can afford. Now look at the left panel. N equals 1 is not simply the smallest case, it is a different case. One measurement has no range inside it. There is no R-bar. There is no sigma hat from within a subgroup, and the whole X bar R machinery has nothing to stand on. So we borrow. The moving range between the consecutive lots become the estimate sigma hat equals MR bar over 1.128. That is the trick the individual chart is built on. It comes with an assumption that consecutive lots are independent, which is in a fab is often false. This is a fab default, not the exception. Metrology expensive, sometimes destructive, and some quantities are simply 1 per lot, which is exactly where we go next. Here is a real IMR chart, H rate, 60 lots, 1 measurement each. Top chart is the individual values with the limits at plus minus 3 sigma hat. Bottom is the moving range. There is a genuine shift at lot 39. The level drops by about 9 angstrom per minute and stays down. You can see it clearly by eye once you know to look. Exactly 1 point actually breaks the limit. 21 lots of a real sustained shift, and the chart's primary rule fires once. Everything else is inside the limit. This is not a defect in a particular data set. It is arithmetic of individual charts, and I want to show you why with a direct comparison. The numbers for that chart: X bar is 996.1, MR bar is 5.24, so sigma hat is 5.24 over 1.128, which is 4.65 angstrom per minute. I chart limits 996.1 plus or minus 3 times 4.65, so 982.2 to 1010.1. That is the band about 28 units wide. MR chart upper limit 3.267 times 5.24, which is 17.1. Now the comparison. This is the main point. Suppose we could afford 5 wafers per lot on the same process. Same sigma, the X bar limits would be plus or minus 3 sigma over root 5, roughly plus or minus 6.2 instead of plus minus 14. The individual chart is more than twice wide. Some processes, some underlying variability, same 3 sigma rule. The only difference what we could afford to measure. The chart you can afford is the chart that detects least, and that is the metrology budget decision showing up in the detection capability. Here it is side by side. Same process, same 1.5 sigma shift at halfway point. Left, individuals limit at plus minus 3 sigma. The shift is there. You can see the cloud move up and almost nothing crosses the limit. Right, mean of 5, limits at plus and minus sigma over root 5. The same shift is unmistakable. The points are outside the limit immediately. Nothing about the process differs between these panels. The shift is identical. What differs is that that averaging shrunk the noise by a factor of root 5 while leaving the signal alone. So the signal to noise ratio improved by root 5. Which is why when you are stuck with n equal 1, run rules matter far more, and the individual's chart needs help, and run rules are the help. Rule 4, a run of one side would have caught this shift within 9 lots. And the second inheritance, the distribution. The X bar chart plots average. So the central limit theorem protects you. And individual's chart plots the raw measurements, so it inherits whatever shape the data has. Here is skewed data, a log normal, which is a reasonable model for many bounded positive quantities in the fab. Draw limits at plus minus 3 sigma. Now count the violations. You should get about 0.135% below and 0.135% above. What you actually get is heavily weighted to one side. Now the consequence. So your false alarm rate is not what you think it is, and it is asymmetric. You will be chasing phantoms on the high side and missing the real excursion on the low side. Nothing about the chart appearance tells you what this is happening. So with individual charts, checking the distribution is not optional diligence. It's part of building the chart. 3 things you can legitimately do: transform, take logs or a square root, or run a box cox. Chart the transform value and convert the limits back into original units for reporting, so the operators still see numbers they recognize. This works well for skewed positive quantities, particle counts, defective densities, and so on. Fit the right distribution. Compute limits for the actual percentile for a fitted distribution instead of assuming plus and minus 3 sigma. Honest and increasingly easy with software. The catch is that you need a lot of data to pin down the tails, which is exactly where you need it. Widen deliberately. Keep the simple chart and set the limits to give you a stated false alarm rate rather than an optimal 3 sigma. Crude but transparent, and everybody still understands the charge. The wrong option is the fourth one: apply plus and minus 3 sigma to visibly skewed data and say nothing. This is not simplicity. That is a chart with an undocumented false alarm rate. But here is the fab's real problem with individual charts, and it is not normality. Consecutive lots through the same chamber are not independent. Chamber state carries over. A run-to-run controller creates correlation deliberately, and this is what is for. Bath chemistry evolves slowly. Everything with memory in the physics produces correlation in the data. This is a stationary process with a lag 1 correlation of 0.8. Nothing is wrong with it. It wanders because That is what the correlated noise does, and it always comes back. Now compute sigma hat from the moving range. Because consequent values are close together, a moving range is small, so the sigma hat is small, so the limits are far too tight. And the chart fires dozens of times on the process that is behaving exactly as designed. The instinct is to widen the limit. Do not. That treats the symptom and destroys the sensitivity you have left. The right answer to model the correlation and charge the residuals. That is the topic of lecture 3. So a checklist. Run this before you trust any individual chart. Is the data roughly symmetric? Normal probability plot, 2 minutes of work, then the skew makes your false alarm rates asymmetric. Are consecutive points independent? Plot each value against the previous one. If there is a visible structure in that scatter, the moving range is lying to you about the sigma. Is there a known deterministic pattern? A seasoning and PM sawtooth is not a special cause. Charting the raw value will generate constant alarms. Chart the residual from the expected cycle instead. Did you compute the limits from a clean baseline? Phase 1 discipline matters more here than anywhere, because with n equals 1, a single excursion moves sigma hat a long way. 4 checks, maybe 20 minutes, and the individual chart is the one that you build most often. So it is 20 minutes you will spend repeatedly. Attribute data, pass or fail, or a count. The structural difference, this is the interesting bit. For continuous data, we had to estimate the spread from data, and that is what R bar over D2 was doing. For counts, we do not have to because the distribution supplies it. If the die fails independently with a probability P, the number of failures is binomial and the standard deviation is binomial. The standard deviation of a binomial is completely determined by P and N. Nothing to estimate. The variability comes free with the model. Now the trap, which is a blessing, a trap in the same breath. The blessing, the limit falls out of the model with no extra data. The trap, if the model is wrong, especially if P varies from lot to lot rather than being a constant, the limits are too tight and the chart alarms constantly on a healthy process. That false has a name, and we will get to it, and it's extremely common. With variables data, you measure the noise. With attribute data, you assume it. 4 charts, you pick by what you are counting. P and NP are binomial. A unit either passes or it fails. One die, one verdict. Pro build is the classic case. Use P when the lot size varies and NP when it is constant, and the only difference is when you plot the fraction or the raw count. C and U are Poisson, a unit that can carry several defects: particle on a wafer, visual defects per reticle die, the wafer with 4 particles and a wafer with 1 are different, and binomial cannot express that. So the answer is, can a unit fail more than once? If no, binomial. If yes, Poisson. Notice P and U handle varying sample size and NP and C cannot. In a fab, lot sizes vary constantly. Engineering splits, partial lots, scrapped wafers, so P and U are what you will actually use. Here is a P chart on real probe data. 30 lots, and the lot sizes vary from about 100 to 50 to 900 die tested. Notice the limits move. They step up and down from lot to lot, and they do that because the limits formula has n in it. P bar plus 3 times the square root of P bar times 1 minus P over n. Small lots, large limit, big lots, tight limit. And that is exactly right, even though it looks untidy. A big lot gives you more information, so you can make a sharper statement about it. A small lot is genuinely more uncertain, and a wide limit is the honest representation of that uncertainty. Lot 20 is above the limit, 8.5% failing against the baseline of 4 point. And that is a real signal because it is a large lot, it is a confident one. The numbers, and there are 2 traps. First trap, the center line. P bar is total die fail divided by the total die tested, pull everything. It is 1384 over 30,100, which is 0.046. Do not average the individual lot fractions. That weights 200 dies lot the same as the 800 die lot, and it will give you a different and wrong answer. Second, the limits are computed per lot, 1 pair for every point. At n equals 200, the limit is 0.046 plus minus 0.0044. At n equals 800, 0.046 plus or minus 0.022. A big lot gets a test twice as tight. And when the lower limit computes negative, which happens constantly at low defect rates, you set it to 0. You cannot have a negative fraction defective. That is not a fudge, it is a binomial being asymmetric near 0, which is also a hint that a normal approximation is straight. Attribute charts are data hungry, and I want to quantify how hungry because the answer changes how you would design a monitoring scheme. To detect a change, it has to exceed about 3 standard errors for a proportion that is 3 times square root of p times 1 minus p over n. At p equals 1% with 500 die per lot, 3 standard errors is about 1.3% points. Your baseline is 1%, so you cannot reliably detect anything smaller than a doubling of the defect rate. A doubling on a chart somebody looks at every day. And it gets worse as defects get rarer, which is precisely the regime a good fab operates in. The rarer the event, the more units you need to see any change at all. This is a quantitative reason fabs chart continuous parameters when they can and fall back to yield only when they must. Yield is the outcome you care about and one of the worst signals to steer by. By the time yield moves, the parametric charge moved weeks ago. Now the failure I promised you. 40 lots from a perfectly healthy line, 3 of them are outside the control limits. If you believe the chart, you would conclude that you have an out-of-control process and launch 3 investigators. Nothing is wrong. The binomial model assumes P as a single fixed constant and every die fails independently. In reality, P varies from lot to lot and different wafer material, different position in the queue, slightly different processing. So the true lot-to-lot scatter is larger than the binomial, and in the limits which were computed from the binomial are too tight. This is called over dispersion, and in high volume attribute charting, it is the norm rather than the exception. The signature is unmistakably once you know it. The chart with lot of violations scattered evenly throughout with no pattern, no clustering, no assignable cause where you investigate. If your P-chart alarms on 10% lots, suspect the model before the process. 3 steps in this order. Test the assumption first. Compare the observed scatter in the p-hat against what the binomials predict. If the ratio is much above 1, you have over dispersion and you know it is the modeling problem rather than a process problem before you touch anything. Then try stratifying. And this is a step people skip. Very often extra validation is real structure that you pulled away and 2 products with different die sizes and 2 probe testers and 2 chambers uplift. Split them, chart them separately, and the over dispersion frequency disappears because you were never looking at one population. Only if the variation is genuinely irreducible lot to lot, widen the model. Use limits based on the observed between lot scatter. A Lani P prime chart is the standard approach. Always try stratifying before you widen. A chart that alarms constantly may be telling you something true and useful, that your population is not one population. The points inside the limits are talking to you. Everything so far has used one rule. Is the point outside a limit? And we have seen how weak that is on its own. 2 sigma shift leaves 84% of the points inside. An individual chart barely reacted to a real sustained expansive shift. But look at what we have been throwing away. Each point carries information about where it sits, not just whether it escaped. 9 points in the row slightly above the central line is individually 9 unremarkable observations, and collectively it is essentially impossible by chance. This is the whole idea of run rules. Use the position of points relative to the central line and use consequences rather than simple observation to build a chart with limited memory. A chart that only checks whether the points fall outside the limits is using a small fraction of the information in front of it. To state the rules, we need a vocabulary, and it is simple. Divide each half of the chart into 3 bands, each 1 sigma wide. Zone C is the closest to the center line, and within 1 sigma, zone B is between 1 and 2 sigma, and zone A is between 2 and 3 sigma. There is a zone A, B, C on each side, so 6 zones in total, and the rule refers them by name. Why zones rather than raw values? Note why this works. Because the zones are defined in sigma, same rule applies to any chart of any quantity of any units. Rule about zone A means same thing on a CD chart in nanometers and an H rate chart in angstrom per minute. That is the Z score from last class doing its job again, one universal ruler. Here they are, the Western Electric rules published in 1956 and still default in essentially every SPC package. The column I want you to look at is the third one, the probability of each pattern occurring by pure chance on a healthy process. Rule 1, 1 in 375. We derived it in the last class. Rule 4, 9 in a row on one side. 1 in 236. Each point has 50% chance of being above the line. So 9 in a row is 1 over 2 to the 9th. Rule 6. 14 alternating, 1 in 4000, very rare by chance, which make it a small signal when it appears. Notice they are all roughly the same order of magnitude, few hundred to few thousands, and this is deliberate. Each rules are turned so no single one dominates the false alarm budget, which raises an obvious question about what happens when you turn them all on. We will get there. And this is where the actual value is, not in the alarm, in the diagnosis. A single while point, something discrete happened in one lot, go to the recipe log, material log, and operator action in that shift. A sustained step, something changed and stays changed. Chamber swap, recipe edit, PM event, a new consumable installed. A steady trend, something is wearing off. Pad, target filament, wall coating filter, anything consumable. Sawtooth with resets, that is a seasoning cycle. Probably not a fault at all, and if you are charting it naively, you will generate alarms forever. Alternating up and down, 2 population interleaves, 2 chamber, 2 testers, or 2 shifts, or a controller correcting a lot. Hugging the center line, almost always a data problem. Overstratified subgroups, edited numbers, stale sensors. The chart never tells you the cause. It tells you which log to open and roughly when, and that narrowing is what makes root cause tractable. Rule 5, 6 points in a row steadily increasing. Look at where the alarm fires. Nothing has crossed the control limit. The process is still comfortably within its band. The chart is already telling you something is wearing off. And that is the value of run rules in one picture. Rule 1 is a detector Rule 1 is a detector of things that has already gone wrong. Rule 5 is a detector of things that are going wrong. On consumable driven steps, CMP sputtering, and anything with an erosion mechanism, this rule frequently gives you enough warning to schedule the maintenance rather than have it scheduled for you. And the caution, on a process with a designed drift and reset cycle, this rule will fire every single cycle. That is the sawtooth case. Either exclude the rule or the chart the residual. Rule 4, 9 points in a row on one side of the center line. This is one that solves the problem we identified earlier. Remember the 1.5 sigma shift that the individual chart could barely see, where 84% of the points stayed inside the limit. Here is the same situation. Rule 1 fires once, rule 4 fires reliably, because after a sustained shift, almost every point lands on the same side of the line. So rules 1 and 4 are complementary in a specific and useful way. Rule 1 catches sudden, large changes. Rule 4 catches small and sustained ones. Between them, they cover 2 failure modes that matter the most. If you ever enable 2 rules and there is real argument for restraint, enable these 2. Rule 6, 14 points alternating up and down. This one has a very specific meaning and almost no false positive interpretations. Real processes do not oscillate point to point on their own. 2 causes essentially. 2 populations interlinked. You are alternating between chamber A and chamber B, or between 2 probe tasters, or between day shift and night shift, and they're not matched. The chart is telling you your subgroups are not homogeneous, or a controller correcting every lot. This is a funnel experiment from the last class appearing in production. An over-tuned run-to-run controller overshoots every time and produces exactly this signal. The diagnostic is easy in both cases. Label the points by chamber, by taster, by shift, and look again. If the alternation lines up with the label, you have your answer in 30 seconds. Rule 7, 15 point on one row inside zone C, all hugging the center line. This alarms people first time they see it, because the chart looks wonderfully, beautifully controlled, no excitement, everything on target. Real processes don't behave this way. If your data is genuinely normal, about 1/3 of your points fall outside the 1 sigma. 15 consequent points, all inside the zone C, has the probability of roughly 1 in 300. So this is not a triumph. This is an anomaly, and it demands an explanation as much as a point outside the limit does. So the next slide, three explanations, none of them is good news. 3 reasons a chart looks too good. Over-stratified subgroups. If your subgroup deliberately spans every source of variation, 5 wafers from 5 different chambers, say, then the R bar is enormous and the limits are enormous and nothing can ever escape them. The chart has been constructed to detect anomaly, usually with the best of intentions. The data has been edited. Someone is rounding or remeasuring anything that looks back or reporting median of 3 attempts. This happens particularly when an out-of-spec reading triggers paperwork, and the chart is often how you find out. The sensor has stopped. A frozen reading, a cached value that is no longer updating, or a gauge that failed quietly on a plausible nominal number. This is extremely common with automated data collection, and it can persist for months before nothing looks broken. A chart that never alarms is not evidence of a good process. It is usually evidence of a broken chart, and it should be investigated with the same energy as an excursion. Before we talk about responding to signals, three things a signal is not. It's not a defect. A lot may be entirely within specs and perfectly sellable. The chart is telling you the process changed, not that the product is bad. Those are different statements, and conflating them leads to scrapping good material. It is not proof. An in-control process throws a point past 3 sigma about 3 times in 1,000. Roughly 1 alarm in a few hundred is genuinely nothing, and you should expect to close some investigation with no finding. It is not a diagnosis. A chart identifies a moment and a pattern. It has no idea what physically happened. That is your job, and the pattern is your hint. What a signal is a prompt to go and look with a timestamp attached. And that is genuinely valuable, and it is also all it is. Every rule is another opportunity to be wrong, and they compound. Look at these numbers. Rule 1 alone, 1 false alarm per 370 points, manageable. All 8 rules, 1 per 40 hour. Chart daily with 8 rules. You are investigating something that is not there roughly every 6 weeks. On one chart, a fab has thousands of charts. And this is the same trade we made in the last class when we chose 3 sigma. You are buying sensitivity to small shift by spending false alarms. The rules are simply a different way to spend the same budget, and they spend it on specific failure modes each rule is tuned to. So the question is not which rules exist, all 8 exist. The question is which failure modes you actually have on this process, and whether each rule is worth its share of false alarm budget. So here is a defensible answer. Almost always rule 1 and 4. Rule 1, a point beyond 3 sigma, is non-negotiable. Rule 4, a run on one side, because that is what catches a small sustained shift, where rule 1 is the weakest. They are complementary, and together they cost you roughly 1 false alarm per 150 points, which is most organization can live with, and add deliberately per process. Rule 5, the trend rule, where you have a known wear mechanism, CMP pads, targets, spotted targets, and anything erosive. Rule 6, alternating, where you interleave chambers or tester, and chamber matching is a life concern. Rule 7, hugging as a data integrity check on any automated feed you do not personally trust. Choose rules from the failure modes of that specific process, not from textbook list. A rule that detects something that cannot physically happen on your tool is pure false alarm budget spent on nothing. One last thing before we leave signals, and it is organizational rather than statistical. An alarm with no different response is worthless. Worse than worthless, it actively trains people to ignore alarms. So every chart in a fad has an OCAP, an out of control action plan. Who does what now? A named owner, what to hold, what to keep running, and who to call, all decided in advance in writing before anyone is standing in front of a stopped tool at 2 in the morning under the pressure to make a shipment. What to check in order, a decision tree specific to that signal on the tool. Rule 1 on an edge chamber is a different investigation from rule 5 on the same chamber. And what gets recorded? A signal, the finding, the action, the outcome. That last one is what turns a chart into a learning system rather than an alarm bell. Over a year, the OCAP record is how you discover which signals actually predict problems on your line. All right, we can now answer, is it stable? So now the next question. Capability compares what a process naturally does to what customers will accept. It is a formal comparison between the voice of the process and the voice of the customer, and it produces a single number. So why does stability have to come first? Because an unstable process has no single distribution. Its mean is moving, its spread is moving. Any capability number you compute describe a mixture of what will not exist next month. You would be forecasting from a process that has no forecast. What capability is not? Two things it is not. It is not a measure of how good the product is, that is yield, and it is backward looking. It is not a statement about this lot, it is a statement about the process's ability to keep producing lots like this one. Capability is a forecast, which is exactly why it requires stability. CP, the simplest capability index. Specifications width divided by the process width. USL minus LSL over 6 sigma. 6 sigma because it is the width that contains 99.7% of a normal distribution, the empirical rule from last week used as a definition of how wide the process is. CP of 0.67, the process is wider than the spec. You are making scrap on both sides guaranteed, no matter how well you center it. CP of 1.33. The spec is a third wider than the process, comfortable. CP of 2.42, enormous margin. And notice what CP does not consider at all, where the process is sitting. Every one of these curves is centered. CP would give you the same answer if they were not. And that is a serious omission, and it is what CPK fixes. CPK, the same idea, but measured to the nearer specification limit. Take the distance from the process mean to whichever spec limit is closer, divide by 3 sigma rather than 6 because you are only measuring one side. Left centered, CP is 1.33 and CPK is 1.33. Where a process is centered, the two indices agree always. Right, the same process shifted by a bit over 2 sigma. CP is unchanged at 1.33. The spread did not change. CPK has collapsed to 0.67. And look at the red tail. That is a real material going out of spec on a process whose CP still looks respectable. Same spread, same CP, completely different defect rate, which is why nobody codes CP alone, and also why you should be suspicious of anyone who does. Now, genuinely useful thing, which is not either index alone and the gap between them. CP is what you could achieve if you have centered the process. CPK is what you are achieving now. So the gap is the centering penalty, and it tells you which problem you have. CP approximately equals CPK. The process is centered, and if the capability is still poor, it is a spread problem, and that is a project, a tool upgrade, a recipe redevelopment, a better measurement system, months. CP much greater than CPK. The process is off target. That is usually a recipe offset, and it is an afternoon's work. Sometimes it is a single number in a controller. This is the asymmetry I flagged in the previous lecture. Centering is cheap, spread is expensive, made quantitative. Two indices together tell you which of those two situations you are in before you commit any resources. Always report both. CPK alone hides which problem you actually have. What numbers actually mean? So the indices stop being abstract. CPK of 1.0 means nearest spec limit is 3 sigma away. That is 1350 parts per million, the same number we computed in the last class. Historically, this was the minimum acceptable, and today is considered marginal. CPK of 1.33, 4 sigma, 32 parts per million. This is a common contractual requirement, and it is what most fabs target for parameters that matter. CPK of 1.67, 5 sigma, 0.3 ppm, automotive and medical. CPK of 2, 6 sigma, 2 parts per billion before any drift allowance, which we will come back to. Every number in that column assumes a perfectly centered, perfectly normal, perfectly stable process. All three of those assumptions fail a little in practice, and they fail hardest in the tails, which is exactly where these numbers live. Treat the ppm column as an order of magnitude, not a prediction. Now a distinction that causes real argument in the industry. Same data, two different estimates. Sigma from within subgroup range R bar over D2 is short term. It captures the variation present within a subgroup over minutes. That gives you CP and CPK. Sigma from all data pool in long term. It includes everything that drifted between subgroup over whole period. This gives you PP and PPK. Look at the difference here. Short term sigma is 0.37, long term is 0.52. CP is 2.16 against PP of 1.54. Same data, same wafer, same measurement. The gap is everything that drifted between subgroups. The day-to-day wandering or that a control chart is designed to catch, and within subgroup, sigma is designed to exclude. Neither number is wrong. They answer different questions. The gap between them is itself informative. So, which do you quote? CP and CPK short term for process development and improvement work. They answer what is this process capable of when it's behaving. That is the right question when you are trying to make the process better, because it isolates intrinsic capacity from control problems. PP and PPK long term for qualification, reporting and contracts. They answer what did the customer actually receive over this period. This is the right question when you are making a promise to somebody. The gap is informative on its own right. CP much greater than PP means the process is stable in the short run and wanders in the long run. That is a control problem, not a capability problem, and the fix is better control scheme, not a better tool. Quoting the flattering one without saying which is the oldest trick in quality reporting. When the supplier hands you a capability number, the first question is which index and the second is over what period. A short detour, because you will hear this number for the rest of your careers. A perfectly centered process with spec limits at plus minus 6 sigma produces nearly 2 defects per billion, not 3.4 per million. 2 per billion, a factor of 1000 better than the famous figure. Where does 3.4 come from? It assumes the mean drifts by 1.5 sigma. Motorola's empirical observation in the 1980s was a real process wander over long run between shifts, between maintenance events, between material lots. They adopted 1.5 sigma as a standard allowance for that wandering. So 6 sigma quality means 6 sigma of margin plus 1.5 sigma drift budget, giving an effective 4.5 sigma, which is 3.4 parts per million. It is a convention with an empirical justification, not a property of the normal distribution. And your process may drift more than 1.45 sigma or less. And when someone quotes 3.4 ppm, the fair question is whether their drift allowance matches their actual data. What is actually expected in a fab? There is no single answer, and that is the point of this slide. Gate CD 1.33 to 2. It directly sets the drive current leakage and the tolerancings every node, while the physics does not get any easier. Overlay, similar targets, harder than it looks, because overlay is multivariate, translation, rotation, magnification, and higher order terms, and the budget is shared across the whole stack. Gate oxide thickness 1.67 or better. The leakage dependence is exponential, so the window is generally tiny. Metal line width at upper levels 1 to 1.33 is often fine, more forgiving geometry. Notice there is no global number. Capability targets are set by how much the parameter matters to the device and how much margin the design gave you. Which is exactly why process teams and design teams argue about them. The target is a negotiation about who absorbs the difficulty. Now a question nobody asks. How much do you trust that CPK? It is an estimate from a sample. So it has a confidence interval, and the interval is much wider than one expects. With 30 measurements, a computed CPK of 1.33 means the true value is somewhere between 0.97 and 1.69. Think about what the range spans. 0.97 is marginal. You would be having a serious conversation about the process. 1.69 is automotive grade. For the same data at the conventional sample size, you cannot distinguish those two situations. With 100 measurement, it narrows to roughly 1.13 to 1.53. Better, still not tight. So when a supplier certificate quotes CPK equal 1.35 from 35 parts, it is telling you almost nothing. The correct response is to ask for n and then compute the interval yourself. Report CPK with its sample size, do not report it. Capability index without an n is not a measurement. 4 ways to produce a confident capability number that is not true. The process is not stable, then the number describes a mixture that will never recur. This is a big one and it is why stability comes first. I have said it 4 times in this lecture and I'll say it again later. The data is not normal. CP converts distance to the tail probability using the normal model. Skew reagents that probability by orders of magnitude and it changes it most in the tail, which is the entire quantity of interest. Too few measurements, 30 point gives you range approximately plus minus 0.35. The point estimate looks authoritative and it's not. The measurement variation is inside your sigma. Every sigma today included in the metrology tool's own noise, you are penalizing the process for your gauge. Then the last one is in lecture 3 and it is the one that surprises people the most. Because of the type parameter, the gauge can be a substantial fraction of the total variance. End to end on the same CT data we started with in this lecture. From the chart, R bar of 0.98, so sigma hat is R bar over D2, which is 0.62 nanometers for this subset. The mean is 45.35 against a target of 45, slightly high. Specification is 43 to 47, so a 4 nanometer window. CP 4 over 6 times 0.62, which is 1.08. CPK, the nearer limit is the upper one. 47 minus 45.35 is 1.65 divided by 3 times 0.62, 0.89. Now diagnose it. CP of 1.08 is marginal but workable. CPK of 0.89 is not acceptable. The gap between them tells you immediately that this is a centering problem, not a spread problem. Which means the fix is a recipe offset about a third of a nanometer an afternoon, and it would be take CPK from 0.89 to roughly 1.08. And this is the entire method from raw wafer to an action in one slide. 3 questions answered. Is it stable? X bar and R for subgrouped data. IMR when n equals 1 with the assumption actually checked. P, NP, C and U for attributes. And read the spread chart first. What is it telling me? Zones and run rules. Each pattern points at a class of physical cause. Turn on the rules that match your failure modes and pay false alarm price knowingly rather than by accident. Is stable good enough? CP for spread, CPK for spread and centering, P and PPK for the long run, always with a sample size attached. And here is what is still missing. It undermines every number on this slide. Every sigma today included metrology tool's own variance. Every control limit, every capability index, every ppm estimate was computed from a measurement system we simply assumed was trustworthy. The next lecture opens there, and when we subtract the gauge, some of today's numbers move a long way.